Okay. Our next topic is moment generating functions. So moment generating functions are in some ways similar, or actually very similar to what we've seen before with um, with probability generating functions. And in fact, they're in a sense equivalent in the case of discrete random variables, as we'll see shortly. So what we're going to do is we're going to let x, so for a random variable x, we'll define a function which we'll write as m sub x, and the argument is t, and we define it as the expectation of e to the tx. So this is the sum e to the tx times the mass function of x over all values of x, if x is discrete. And this is the integral of e to the tx density of x dx if x is continuous. Okay, so remember how we recall the probability generating function, which we define as gxt, was the expectation of t to the x for a discrete random variable. There's similarity to that, and we'll see that in a moment, but it is not exactly the same. Okay, so something to observe here is that if I put 0 in, e to the 0 is 1, so moment generating function evaluated at 1 is evaluated at 0 is 1, and the moment generating function evaluated at t is infinite if the sum or integral diverges, and in that case, that's going to kind of mess us up a little bit, okay? But the idea behind moment generating functions, as it was for probability generating functions, is that we can interchange the order. So as long as we can interchange the order of an expectation and a derivative, we're in business. What do I mean by that? Well, let's consider the first derivative of the moment generating function, right? Is d dt of expectation e to the power tx, which, as long as we can bring that derivative inside, and we can't always do that, but in the cases where things work out, we can do that. So if we bring that on the inside, we have d dt, we have a derivative with respect to t of e to the tx, which is easy for us to do because e to the tx has a derivative of x. So it's just x of x e to the tx. Second derivative e to the tx of, sorry, is the first derivative of the first derivative. So x e to the tx. This is, again, if we can bring the derivative inside, this is the expectation of d dt of x e to the tx. We just bring another x down. So it's the expectation of x squared e to the tx. And so on. The kth derivative can be expressed as the derivative of the k minus first derivative of t. And if we do that out, we're going to see by induction, this is expectation of x to the k e to the tx. So what's significant about this is if we evaluate each of these derivatives at 0, then the derivative at 0, right, is equal to expectation x times e to the 0, which is 1. So this is just expectation of x. The second derivative at 0 is expectation of x squared. In general, the kth derivative at 0 is expectation of x to the k. So that's the sense in which this is the moment generating function. We call this the moment generating function precisely because, in a sense, it generates the moments, or it records all the moments that are easily obtained by taking derivatives with respect to t and then evaluating at 0. So this is valid as long as this function is finite for all t less than some epsilon. So it doesn't matter how small, as long as this is finite in some window of t, we're okay. And this is called the moment generating function of x. So the moments are important, and the moments in a lot of ways tell us everything we want to know, and in some cases everything we need to know about a distribution. We just have to be careful in some cases. But the moment generating function is a very useful example, well, a very useful function, and we'll be deriving some properties of that in this chapter.